Hello, everyone, and welcome to today's webinar, Field Testing Next Generation 5G Developments. Thank you so much for joining. Today's speaker will be Russell Lindsay, Senior Product Manager for Rtsa Company. Just as a quick note before we get started, please do ask any questions at any time. We'll do our best to answer it via text or afterwards at the last minutes of Q&A. And we will be sharing with you slides as well, so please do keep that in mind. With that, I give you Russell Lindsay.
Great, thank you, Ben. And thank you everybody for joining this morning, or for those of you watching in a recording for taking the time to listen. We have been doing a lot of 5G testing around the world in every continent over the last 2 years or so, and we're looking forward to sharing with everybody our results. The way we're going to break this down is I'll give a little overview of what we've seen around the world. Try not to spend too much time on that. You know, I know sometimes we feel like we're drowning in press releases, but we'll give some of the pertinent information and then do a little bit of an overview of the 5G radio technology and how that plays into then the considerations for field test, and then give an introduction of our new offering from Rtsa. So as I mentioned, we've been around the world doing testing. I know everybody's attended 100 webinars about 5G, so I'm not going to spend too much time on this. But the main things that we've seen around the world, obviously in Korea, with their major launch, the government mandated that the 3 major carriers get together and prepare for a March launch of the world's first 5G mobile network. They did launch with enterprise customers in December, and now are getting ready to launch here in March. So we've been supporting that bring up with our instruments. They're doing a lot of testing. It's been a great opportunity for us to learn about the requirements that are going to be there in field tests, and we've leveraged a lot of those learnings into what we're going to share today. A lot of work then happening in Japan, getting ready for the Tokyo Olympics in 2020, and doing testing on things like their high-speed rail to try to keep high-speed networks there as people travel across the country, and then in the denser city networks. So I think the spectrum auctions are actually happening there in the next few weeks. And then, of course, in the US, a lot of work in the fixed point wireless and mmWave. This is really, it's actually kind of an interesting contrast where most of the world has been focused on their work in the sub-6 gigahertz bands. The US has been leading the way in the mmWave. There's been some activity sub-6, it's mostly below 3 gigahertz. And then we have a lot of trial networks that have been built out, mobile access points, and there are actually a few live customers here there in the US. A lot of activity in the European Union. There are trial networks all over the regions, the UK, Spain, France, Germany. Again, this is initially mostly the sub-6 gigahertz with commercial launches coming in 2019. In China, they're now launching their trial networks in the sub-6 gigahertz bands with mmWave planned for later this year or into next year. And then single carriers are announcing right now that they're planning on installing upwards of 50,000 G-Node Bs around the country over the next couple of years. And then, of course, those aren't the only countries. There are countries all over the world with carriers everywhere, from Canada, Turkey, Australia, who are already building out their networks that we've been working with them and learning from them. So that's what we're seeing in the world. So with that information, we want to take some of that and discuss set of foundation for 5G technologies, because I'm going to share with you some of the learnings and some of the considerations we want to give you on test. But before I do that, I want to make sure we all start with a sort of foundation on 5G radio technology. So there's a few differences in 5G from some of the older wireless technologies that play into the field test world. The first being that we're entering into new frequencies and we've changed the physical layer characteristics. So we have new bands that have been opened up globally. Those are, I mentioned, which I'll describe here in a second. Those are the sub-6 and the mmWave. These new frequency ranges open up the opportunity for wider bandwidths and a restructure of the physical network, which maximizes network efficiency. But it does introduce regulatory challenges. Things like propagation losses and other commercial issues also come into play as well. Also different with 5G is now the structure of the antennas. The antennas are now, rather than transmitting omnidirectionally, these are antenna arrays that utilize and the array technology utilizes massive MIMO with things like multipath or overlap. So each of those arrays now, when you're dealing with all of these antennas and they're using dynamic phase shifting for creating beams, you now have some different challenges in how you can test those things direct connected or over the air, which we'll discuss when we get into testing. And then finally that leads into beamforming and SSBs. So most of our transmissions in 5G, most, not all, but most of them are going to be beamformed versus omnidirectional. So you'll have a radio that's transmitting anywhere from 8 to 64 low-level sync signal beams. The established connections with your UE, once the connection is established with the UE via the SSB, then data can be transmitted between the two. And also, because it's only happening with the connection with the beams, you're only going to get data when you're in that direct beam. So I'm going to break some of this down into their different parts a little bit more. To start with, I mentioned operating bands. So this is all based on the 3GPP working documents. So when we talk about operating bands for 5G, we're really looking at two frequency sections, FR1 and FR2. FR1, which if we kind of look at this in a different way, FR1 is what we typically refer to as your sub 6 gigahertz, and FR2 being your millimeter wave. The most common bands that we've seen in the world as we've done our testing, in millimeter wave, we've actually seen anything from N257, 58, 60, or 61. They're all being used and deployed in the world today. And then in your sub 6 FR1 bands, it's the most commonly, the common bands that we've seen are actually N77 and N78. And then N79 will start to ramp up as China releases their frequencies to the carriers. Taking that further, beyond just knowing your band, you have to be able to define the center frequency, and I mentioned the SSBs. Those are key characteristics of understanding your signal. The center frequency can either be defined as just a frequency, or according to the 3GPP definition, it's defined by the absolute radio frequency channel number. So within the 3GPP document 38.104, it gives all of the different the ranges for ARFCN for each of the different bands, and then those can be calculated. The center frequency can then be calculated based on this equation you see here on the screen. And then breaking that down even further, within that center frequency, you also have an offset of your center frequency and your SSB, and that is defined by the GSCN, the Global Synchronization Raster Number, which can be calculated based on the equations you see here on the table here. So this is kind of these are the slides that you ignore and then read later. So I'm going to try to explain them a little bit better with some graphics here in a second. And then the final piece of it within the definition is your subcarrier spacing. So it's important to know and understand within your 10 to 100 megahertz wide signal, how much spacing do you have with your subcarriers. The most common that we've seen are 30 kilohertz. That would be in FR1, and 120 kilohertz in FR2. And we've also seen some mixed 120 and 240 in FR2 as well. So practically, what does this look like in the frequency domain? So if you have your band, which can stretch several hundreds of megahertz, you then have your actual center frequency and bandwidth, right? So let's say you have a 100 megahertz wide signal. Your center frequency is then defined by your ARFCN, and then you have an SSB, which really identifies your signal, and the offset between the center frequency and the SSB is then defined by your GSCN. And then on the physical layer side, the 5G NR signal is broken down into 10 millisecond repeating frames. So each frame is 10 milliseconds, and that is always true of a 5G NR signal. Those frames are broken down into 10 subframes. So 10 1 millisecond long subframes, and that's a constant that's always true. And then each subframe is broken up into a number of slots, and the number of slots is defined by the number of subcarriers within the subcarrier spacing, the SCS within your signal. So that can be from 0 to N. I think typically we've seen 2 to 4 slots within a subframe. And then each of those slots is then broken down into 14 symbols. And basically the time length of the slots and the symbols is defined by your subcarrier spacing. So if we look at an example of this, a graphical example of this, so if you look at this diagram here, at the top you see this is a 1 10 millisecond frame broken into 10 subframes. So at the top you see SF0, SF1, SF2, those are their subframes. And then each of those subframes is broken into 2 slots. And then within those slots you have the symbols that give different pieces of information. So this is an example of band 78 with a subcarrier spacing of 30 kilohertz and 100 megahertz of bandwidth. So that subcarrier spacing of 30 kilohertz then defines that there are 2 slots within each subframe. Within this diagram, we can then break it down into its 2 different components, one being the SSB, the synchronization signal block, and the other half, or the other portion of it, the other 80% in this case, being the data. So if we look at each of those pieces, first we'll look at the synchronization signal block. The SSB is, if you look at this on a symbol side, if this is one of your slots with the 14 symbols, contained within this slot is your primary synchronization symbols, your secondary, and then also your broadcast channel. That information is what is used to determine the characteristics of the cell that you're testing. So this is where you get things like your cell ID, the beam ID, and then the power levels of that SSB. And then if we look at the other side of this, the data side, this is where actually I think 5G NR gets really interesting and almost a little bit mind-boggling. In this case, in the example that we're using here, where we have 8 subframes to work with in our data, those subframes are broken into, or excuse me, the symbols within those slots are broken into uplink and downlink. And the uplink and downlink, in this case, you have 10 of your slots are downlink, 2 of them are uplink with a guard band in between them. That data there can be actually configured in up to 56 different ways, and even more actually in the future, where you can have slots. Some slots are either all downlink, some are all uplink. There can be a mixture, all depending on the different, they really be dynamically changed based on the amount of interference that you have, the amount of data on the network, and what's really crazy is that these can change every 10 milliseconds. So you could actually see these dynamically changing, and the radios are going to be smart enough that as they look at their UEs and as they try to maximize and optimize the network, they're going to be regularly changing the configuration of these slots. In this case, the one we're looking at here is this is format 32. So you see, just like I showed, you have the 10 downlink frames, the 2 flexible guard band frames, and then the uplink. So now I want to show you, this is where it gets kind of fun. This is an actual capture. With our instruments, we took them out in the field, measuring some trial networks, and we were able to capture the data from a live network. And we took that data and we were able to see, this is what we kind of translate into a spectrogram view. And so if I translate this into what I was showing you before, this is a 30 millisecond capture. So you see there are 3 frames within the capture. Inside each of the frames, you see here are my sync signal blocks. Now, the sync signal block, by definition, by 3GPP definition, can repeat either every 10 milliseconds or every 20 milliseconds. In this case, this was a radio that was repeating the SSB every 20 milliseconds. And then you also see a little bit of downlink there. So that's where these sharper yellow lines, that's where we see some power from downlink. So if I take that and I flip it on its side and look at it in the frequency domain, essentially what I'm looking at now is that my center frequency and my SSB are lining up. So I have a 0 megahertz SSB offset. So just to visualize, I've basically taken this diagram, flipped it down on its side, and you're able to see where that SSB resides. Here's another 3D look of that, where basically you have RF energy in time on your x-axis, showing you showing you the SSBs popping up and the different power levels of those SSBs, and then the downlink being the brighter, larger pieces that take up more of the frequency bandwidth. Here's an example just to show you a few of the other examples that we've seen as we've done testing out in the field. Here's an example of a signal that is actually repeated every 10 milliseconds. So I mentioned above with our original example, this one is repeated every 20 milliseconds. That's the yellow there. This one has a different color scale, but if you see, if we're looking at the top here, the yellow sections here, those are our SSBs. And if you look at our time scale, those are now repeating every 10 milliseconds. So this is just a different interpretation of the radio based on the network requirements for this radio test. Here's a real world capture of a signal where we have an SSB offset. So the center frequency being at 0 in your y-axis, and then the SSB being down here. Basically the distance in frequency between the center of the signal and the center of the SSB, that's your offset. So again, if going back to our original diagram, if I take that, flip it on its side, show it this way, essentially your SSB offset is now defined by the frequency difference between the center and the center of the signal and the center of the SSB. Also, something that's kind of interesting about this signal is this is one that only has a single SSB. That's not common. It doesn't comply with what you'll see in commercial deployment, but we've seen in some test networks, just for test purposes, at times we're only transmitting a single SSB. We'll talk about that a little bit more when we get to some of our considerations for test. A couple other quick examples. This is a capture of a mmWave signal where you actually have more than 8 SSB beams. So typically when we're looking at FR1 signals below 6 gigahertz, and they are compliant for actual mobile data, you'll see 8 SSB beams. When we're looking at mmWave, it can range from 8 to 12. We've seen 12, we've seen 18, and we've seen all the way up to 64 beams. And those beams, because we're using the wider subcarrier spacing, you now have your SSB is now going to take up more slots. There's going to be more slots per subframe, and you're going to take up more subframes for your SSB. So it's going to take up a bigger portion of your total bandwidth just in the identification phase of that signal. This is another example. This one is the SSB is shifted to the other side, but you can see a little bit more clearly the difference in the SSBs. You can count through there and see something. I think there's 18 SSBs there, if I remember right. So basically how this translates then into the real world is when I have my radio, my 5G radio out in the field, it's going to be transmitting to a sector. Typically it's going to be around 120 degrees wide. And then the SSB beams will be distributed evenly among that sector. And the UEs, or the user equipment, those are the cell phones, or in the case of a fixed point wireless, they call them CPEs. Those are the access points that are in the home that communicate with the radios. They basically will identify themselves to the radio based on their position within the SSB. Based on their position there, they can the radio can then pick a data beam and direct a beam directly to the UE to give that data. So that's where it all leads, starting with the bands and the frequencies to the GSCN, ARFCN. That all leads basically to this protocol where you get communication between the radios. So with all of that baseline, we want to give some of our learnings, some of the things that we've done with the field test, so that going forward, hopefully what we discuss today will help you as you go prepare to do field or lab tests of 5G NR, some of the challenges that we've seen and some of the things that we think you should take into consideration. So the first thing we want to talk about is you really should know your radio or know your signal. It's actually been kind of surprising to us how often we've gotten out to do testing, and this is no criticism of any group or person. This is just a sort of a fact of new technology, but there's been a bit of a disconnect, I think, between when somebody gets a radio and knowing and understanding what's actually going to be coming out of that radio. They're given some basic instructions on how to control it, but maybe not prepared to understand everything about what's happening in the RF world. So when you go out to do testing, it's really critical to understand the bandwidth of the signal you're transmitting, the center frequency, or preferably knowing the band and the ARFCN, and then knowing the SSB offset, or again, preferably the GSCN. And based on that data, we can then understand the positioning of the signal. And then the subcarrier spacing is critical to understanding the physical layer configuration. And then also understanding whether your radio is transmitting the standard, the NR standard, or it's using the TF or non-standard waveforms. And even within NR, I should mention that there have been several releases within Release 15. The definition of the NR signals, there have been a few releases that have made changes to that physical layer structure that can impact the way those signals are read. So, for example, in 2015, there was a March release and a September release. And so knowing if your radio has been updated with the September release or even the next release after that, it is key to understanding what's happening when you're making measurements on that signal. And then, and by the way, from what we've seen in the market, 2018 was definitely a transitional year. It was kind of a slog, really, honestly, getting hardware built up, and then taking that hardware and transitioning it into the NR waveforms. But as we ended 2018 and are now getting through the beginning of 2019, it seems like people are really finally starting to get standard hardware with the standard waveforms. So it's actually, I think we've kind of gotten over the worst of it, where we're really now pushing forward into installation and test, and everybody's standardizing on the same thing. So if you're a part of that, you can pause for a second and pat yourself on the back. I think it's been a lot of work for everybody in many different industries over the last couple of years. And so it's nice to see it all coming together. I've also highlighted in green here on the left-hand side 2 other things that I think are valuable to know. They're not required for test, but understanding the number of SSBs in your signal and the data configurations you have in that signal are going to help you do testing. And this is just because, again, when we're doing test systems, it's possible for a test system to do things. It can tell you the number of SSBs. We could possibly even give you the SSB offset from the instrument. But when you have the test instrument giving you the data, you're no longer relying on the test instrument to tell you to give you the quality of the signal that's being transmitted. We're just telling you what it's doing. We're not telling you if it's doing what it's supposed to be doing. So we rely on the person doing the test to understand the correct setup of the radio, so that then we can tell you whether it's transmitting the way you expect it to be transmitting. And that especially goes for the SSB offset. Because, for example, one of the major measurements that you're going to make, I have these on the side here, on the other side, one of the major measurements you're going to make is the frequency error. In order for us to tell you, the frequency error is basically the difference between the center of that SSB where it is and where it should be. We can measure, if we went and if we auto-detected the SSB and we basically set where we think the SSB is going to be, all we're going to do is set that frequency error to 0, and you won't know whether that reading, whether your signal is actually transmitting at the frequency you expect it to. So you're not going to be able to test that factor. So that's one example of why it's important to know. But with all that information, you can then pull out your cell ID, your beam ID. I mentioned frequency error. We can give you time offset. RSRP, RSRQ of your beams, and EVM. So the most common thing, honestly, going back to what I just said, the most common test problem that we've seen in the field over the last year and a half that we've been doing testing is an unknown SSB offset. It's very common for the people doing the tests on the radios to not understand the signal that's being sent out. And like I said, we can help you derive that information and help you continue with your tests. But the more valuable way for you to make your tests and understand your tests is to know from the radio manufacturer what the correct SSB offset is, so that we can then help you measure, or even preferably the ARFCN and the GSCN. I also have a couple examples here of another common problem that we've seen also related to the SSB. Before I reveal what it is, I'll give you 3 seconds to look at it and play detective based on what we've discussed. See if you can determine what's wrong with this signal, or why this signal would be difficult for us to measure. Everybody in the room is waving at me. They know the answer, but but basically what we see here is that there is no SSB, and this is another very common issue that we see with signals in the field, where someone goes to make a measurement and they say, well, I can't get sync on the signal. I'm not getting any of the information. And so the test equipment is bad. It's not the test equipment it's bad. The fact is that the test equipment relies on that SSB to identify the signal. And in many cases, the radio is not transmitting that SSB. The case on the bottom is a mode that we call OCNS, where essentially the radio is loaded with a bunch of dummy data to basically use for power measurements, where you can measure what is the maximum amount of power that's going to be coming out of my radio. That's really valuable, but based on the 3GPP definition for these test signals, they are not required to include the SSB in there. And so, yes, we can continue making a lot of very good RF measurements, power level measurements, frequency measurements. We're not going to be able to decode the signal without that SSB. Let's see. So then moving on, the next thing, apart from knowing your signal, it's also very important to know your environment. So I have a couple examples here of signals, radio placements. You may be at the top of a building. You may or may not have access to the top of that building. If you do, you can make measurements from the backside. If not, you're going to be, you're either going to be right behind the antenna, or you're going to be 100 meters away from the antenna on the ground. So understanding where you'll be making your tests are important. This is an example of radios that were actually hung around a stadium. And what's important to understand here is, notice that one of these radios in here, I believe it's the one on the left, is a 5G radio. But the others along there, the other 5, those are legacy networks. And so when we went out to do this test, we were getting a lot of RF overloading the front end of the instrument, because there's just a lot of other signals, a lot of RF in that environment. So understanding the different frequencies that you have and being able to set your instrument properly is important. And then this is an example of a rooftop test site where you notice there's the red chain at the bottom there. When you're going to do your testing, these radios, while 5G radios will certainly not pose when installed correctly, will not pose a health threat to the environments, there is, just like any other radio, a danger in being too close to the signals right in front. And so being sure to understand where can I stand, where can I test, where is it safe to be, those things are all very important. So also, the environment is going to play really into whether you're doing your tests over the air or whether you're doing them direct connect. So breaking those down a little bit, with direct connect, it's a bit of a paradigm shift from what you might be used to with LTE testing, where you had a single RF test port that basically tapped into the omnidirectional radio and told you everything you needed to know about the power levels of the signal. Now, with these radios, the radio manufacturers have been mandated to build in coupled couple test ports, but there's still not a lot of alignment on what that really means. Do I couple a test port off of every single antenna element? Do I somehow couple and aggregate all of the antenna elements into one? Every antenna element has an amplifier. So am I coupling before or after the amplifier? All those things. I mean, obviously, after the amplifier is the only way you're going to get a valuable measurement, but then that's going to impact your signal integrity. So those are all important considerations. The common test that we're going to see with Direct Connect, this is really going to be where in countries that have regulatory requirements during installation, they're going to ask you to run through the 3GPP requirements for the radios for things like channel power, occupied bandwidth, ACLR, which tells you what sort of power leakage you have into other channels, frequency offset, like I mentioned, and then unwanted emissions is very important as well. Not only understanding how you're impacting your neighbors. So, am I, with my spectral emission mask, am I leaking out into adjacent channels where other carriers or other types of technologies might be? But also the spurious. We're opening up brand new frequency levels, and the impact of those into other technologies in other frequencies is going to be a factor that we're going to have to adjust to, and making sure that we're not impacting with the spurious and harmonics. Specifically the harmonic testing, we're not going to be bleeding into other frequencies. And then over the air is really a whole new challenge. It's a different beast altogether. The common tests that are going to be done over the air are things like coverage mapping, indoor and outdoor, positioning of the radios. So you see the diagram I have here in the center of the slide where if I have a radio that's transmitting 8 sync signal beams, by using the instrument, and a directional antenna, I can basically follow the pattern of that sector, that 120 degree sector, and I can ensure that the beams are pointed in the direction that I expect them to be pointed, or even in this case, in some cases, understanding what the multipath is. We had a case where we were testing like this, and the beam power at beam 0. You saw what you expected in the histogram, where, like you see here on the left-hand side of the instrument, where at beam 0 you have higher power, and then as you move further around the sector, you get higher power towards beam 7. But we actually saw a lot of power from beam 0 because it was reflecting off of a building. And in 5G networks, that's going to be important information in understanding how to optimize the network. So some of the major, and then some of the other tests that are happening are things like time offset. So it's the timing of the instrument, or the timing of the radios. The radios should all be timed to a GPS clock. So the start of the 5G frame that we showed you earlier in the physical layer should be synchronized to the beginning of the GPS clock within a certain number of microseconds. I think 2 microseconds is the spec. And so being able to take a measurement over the air and understanding, as I get 100, 200 meters away from the radio, with the propagation, with the change in time, even connected to the radio, is my frame synchronized to that GPS clock? And then power measurements are going to be a whole other challenge as well, because actually, let me, if I jump to the next slide here, the reason why power is going to be a challenge is, again, it's a paradigm shift from LTE, where with LTE you had a radio that's transmitting omnidirectionally into a sector. Let's say it's the same 120 degree sector. And if I have all of these cell phones out that are connected to my radio, every bit of data that goes to the phone at the top of the screen, the RF power that goes to that one also goes to the phone at the bottom of the screen, and for that matter, to a piece of test equipment. So all of that RF energy, here's my really fancy animation, all that energy goes into your instrument. So you could stand anywhere technically and make the measurement. With 5G, that's going to be a different challenge, because you can stand anywhere in that sector and make measurements on your sync signal block, assuming it's functioning properly. But when the UE, or once the radio makes connection to a UE and starts sending data, that data is going to be sent directly to the UE. And so if I'm standing in a gap not near the UEs, I'm not going to know or measure any of that data that's coming across the network. And then coming back here, the other issue here is with these signals being beamformed. Excuse me. With the signals being beamformed, you have a different shape of the signal, and so a typical measurement in the field has been, well, I can go out and I can make a channel power measurement, and I can aggregate that back to what is the total radiated power from my antenna. That's no longer true with a beamformed signal. If I make a channel power measurement at a certain spot, there's some calculation involved in understanding what that total radiated power would be for an omnidirectional antenna. So that's called the EIRP, the equivalent isotropic radiated power. And so that's going to be the over-the-air power measurement that's going to be made versus just a typical power measurement that you would get on an LTE radio. So some of the considerations when planning for testing in the field, you should know whether you're in the far field or the near field. The beam in an LTE radio is not fully formed until it's in the far field. So you're not going to make a valid EIRP measurement in the near field. So you want to make sure you're outside of, and also for safety, of course, but you're going to want to be 10 to 15 meters at least away from your antenna. Also, the antenna that you use is going to be an important factor. If you're doing something like coverage mapping, you're going to want an antenna that is omnidirectional, because you're taking in the RF energy. You even with multipath, you're going to want to understand where you're covered as you go through and make your measurements. So if you had a directional antenna, you're really only getting a sector of the measurements, and you would have to somehow keep it pointed at the radio at all times. With an omnidirectional antenna, you're going to get that RF energy from everywhere. But if you're trying to do things like positioning and making sure that the radio the beams are pointing the way that they are expected to be pointing, or if you're trying to do test measurements on one specific radio and specific beams, you're going to want a directional antenna to match the directional nature of the beams. Another issue, these signals are polarized. The nature of the beamforming means that these signals are polarized. Now, in the field, we found that the further you get away, the more multipath, the less impact you're going to get from polarization. But if depending on what you're trying to do, there are studies ongoing about if I have a directional antenna that's polarized, trying to make sure that I capture energy from both polarizations, and aggregating that data is a consideration you're going to want to make. Okay, so really to summarize, when it comes to test, what we're saying here is that you should know your signal. The more you know about your signal, the more valuable the measurements are going to be. Make sure you understand your results and know what you're getting from things like RSRP. What does it mean to have different beam powers in different areas? Understanding your G-Node B architecture. How are my test ports coupled? What is the impact of the performance? How am I going to make these regulatory tests that are required of me? Make sure you're picking the right antenna and know the right place to make your tests. And then, of course, you have to have the right test equipment, which is where we come into play. So now's the time where you sit and listen to all the awesomeness that we have to offer from Rtsa. So this is our new Fieldmaster Pro, which we just introduced at Mobile World Congress a few weeks ago. This instrument is prepared for the 5G world with 100 megahertz of analysis bandwidth. It has demodulation capabilities built in for the 5G signals. So all of that information I told you about the SSBs, this instrument takes those SSBs, demodulates them to provide you with the beam ID, cell ID, SINR, RSRP, RSRQ of your SSB beams. So here are the measurements that we make. It does have the multi-beam view to allow you to do the directional pointing, gated sweep for those TDD type signals. And it is prepared with built-in software for the over-the-air measurements. So for example, EIRP, we do the calculations for you, so you can take that channel power, we convert it to EIRP. We also work with our neon coverage mapping solutions to provide 5G indoor and outdoor coverage mapping. So we can give you basically indoor and outdoor maps of your beam coverage, beam by beam, to let you know where am I getting signal to the UEs, where am I going to make proper connection with the UEs. We come in several different frequency models, from 9 kilohertz up to, on the low end, 9 gigahertz up to the high end of 54. So whether you're testing in the FR1 or FR2, we have an instrument that will cover your needs there. And importantly, you know, we're able to provide you with that full frequency coverage. So when you're making those measurements of understanding your impact in the harmonics or interference in other bands, you can make those measurements with this instrument. It's ruggedized. It has a ruggedized industrial design. So ruggedized connectors on the top with a rubber overmold housing over the top. It is built with a cold rolled steel frame, and it now is built with a 10.1 inch all capacitive touch screen. So basically moving into this touchscreen world where you can now drag your center frequency, pinch and zoom for span, drag your markers, and that screen itself is a chemically strengthened soda lime glass with an anti-reflective coating. So we've put this instrument through the ringers, made it ready for field test, so it can withstand your environments. It is best in class in frequency range, DANL, and then things like TOI and 1 dB compression to help you with any sort of distortion on your front end, and amplitude accuracy. Just to give you a couple of screenshots of what we do, relating back to the measurements that I talked about before, all of those channel frequency and power measurements that I discussed, channel power, occupied bandwidth. Here we're showing an example of an ACLR measurement, measuring your signal leakage into other channels. Of course, spectral emission masks based on 3GPP definition. The gated sweep. So if you go back to, take your mind back to the diagram of the frame structure, where I have uplink and downlink that's mixed within my subframes. When we have defined test systems, if I'm making a measurement out in the field, the only thing that I care about, I'm caring about the energy coming from the radio, from the antenna into the environment. That's all downlink. The uplink is what's coming from the cell phone, going from the cell phone back to the radio, which isn't as important of a measurement in the field. So by using a gated sweep, we're able to then look at the signal in power versus time. And as long as you have a repeating frame structure where your data always resides in the same slots or subframes, you can then gate the measurement strictly on the downlink. So when you're making any sort of channel power measurements, like by bandwidth measurements, you know that you're only making measurements on the downlink. I mentioned the full frequency coverage, so you can make measurements like, according to the 3GPP spec, radios should be measured up to the 5th harmonic, or up to 12.75 gigahertz or the 5th harmonic, whichever is higher. So being able to make that full measurement at the correct power levels. This is the multi-beam view. This is actually what I'm showing you here on the screen is a real capture from that test network that we showed. This was the picture of the radio on the stadium, where we walked the sector and were able to see the power levels change of the different beams and measure the coverage. And then here's an example of the EIRP, where we provide you with the live EIRP value, a max hold EIRP. The reason why we do the max hold is if you imagine yourself in the field, you're pointing an antenna, you're pointing a directional antenna at the G-Node B radio, or at the antenna, the transmitting antenna. It's going to be a bit of a transition understanding where those beams reside. And so if my number one goal is to go out there and make an EIRP measurement to understand, at some distance, what is the most power that I'm putting into the environment, into the atmosphere? I can take that antenna and I can run it through multiple angles and positions, and basically by keeping that max hold, we tell you, okay, well, within this area, this is the maximum amount of power that you would see in your area. So that's basically the summary of the instrument, and actually the last slide that I have. So I think now we'll go ahead and do some questions. Let's see. Let's start with what I have here in the chat. So the first question I have from Evan Jones. So the SSBs identify the individual UEs and tell the antenna array. I'm sorry. Oh, I'm sorry. I guess this one was answered online or over the chat. Let's see. The metrics or measurements we can get in real-time spectrum analysis. So I guess the question is what is it that basically what are the benefits of Rtsa in 5G radio testing? So yeah, I did mention that the instrument we're announcing has Rtsa. The way that you would use Rtsa in 5G field testing is with the Rtsa, you're able to capture a lot more of the data from the frame. So for example, what we showed you, where I showed you the spectrogram of the frame, that allows you then to identify where your SSB is. Because if you think of what a typical spectrum analyzer is doing when it's sweeping, it's basically taking thousands of samples, and depending on the detector that you've chosen, it's either giving you the peak value from those samples or the average of those samples, and then giving you a single data point at a single amplitude value at a data point. What real-time does is it actually takes all of those thousands of samples and lets you see what's happening at a much, much more granular level. So a typical spectrum analyzer, it's going to be really hard for you to see where that SSB is. With real-time spectrum, with an Rtsa, you can get a better feel for your SSB. The other thing is it's very important, the timing of the signals is very important when either you're in a crowded space. So you think about, we're offering 100 megahertz bandwidths to carriers, to multiple carriers in a single country. Basically, in order to make most efficient use of our frequency bands, they're going to keep those as tight together as they possibly can without causing interference. And so it's important that each of those signals meets its timing requirements on GPS. And so with something like Rtsa, you can get a much better feel for any sort of timing difference between, let's say you straddled the bandwidth between two carriers, whether they're a single service provider with carrier aggregation or whether they're a couple of different service providers. You can actually see the timing difference there between those signals, which is going to impact the interference between those signals. Let's see, will there be a key or legend for all the acronyms? That's something that we can, I think, provide. Let's see, but actually, before I go on, Ben, did you have any other questions that you wanted to bring out?
Yeah, thanks, Russell. And yeah, everyone definitely keep asking some great questions. I wanted to know, what are the benefits of a real-time spectrum analyzer when it comes to 5G measurement?
Yeah, so I think I basically covered that one with the last question. Like I mentioned, it's really understanding, being able to see the timing of the signal. It's being able to see the components of the physical layer broken down into more of its parts. Okay.
And if your current spectrum analyzer recovered 43 gigahertz, and most 5G developments will happen in the sub 39 gigahertz frequencies, why would someone need a new instrument?
So that's a fair question. Obviously, there are a lot of spectrum analyzers out there, and Rtsa has been selling many 43 gigahertz instruments for a lot of years now. The big difference here is that as we go into the wider bandwidths, the wider capture bandwidth of the signal is really the important part. So being able to, as we get into the data of the signal and understand the full characteristics of the data and the SSB on the signal, you want to be able to have it's important to have a modulation bandwidth that matches the bandwidth of your signal. So that's why the transition here from a legacy technology for LTE testing is important to getting into something newer.
Awesome. And why does the network need to be tested with the spectrum analyzer instead of just a UE?
Yeah, I get this question a lot. And I think testing with a UE has its value. A UE will provide you with some of the same information like an RSRP or an RSRQ. It gives you some level of understanding of coverage, but it's not going to do the same thing. It really isn't built to do the same thing that a piece of test equipment is built to do. So it's kind of the wrong tool for the right job. It's the protocols that are built into UEs aren't meant to try to differentiate the beams the way you might expect them to differentiate them. And they're also really fundamentally important is that they're not calibrated instruments. So really it's not important when someone designs and manufactures a UE, they certainly they put a lot of effort into the engineering of the protocols to make sure that the throughput is maximized, but it's not as important to them to understand the power level, to really accurately portray power levels and things like that. So a piece of test equipment is really designed, built, manufactured, calibrated to make the types of measurements that you're looking to make in the field and that regulators are requiring you to make.
And what applications are going to be the most important to 5G?
Boy, I think if anybody knew the right answer to that one, there are a lot of things. Verizon recently actually did a competition for people to submit their ideas, and they're offering funding for the people with the best idea for 5G, because what we all see 5G as is, well, how can I use it with my cell phone? And there will be a value to that, certainly as the networks progress, but I'm not sure we even totally have the application yet today that's going to be the most valuable for 5G. So it's going to play into a lot of things like self-driving cars and the efficiency of roadways, things like remote construction sites and remote surgeries, and all the kinds of things that seem like super futuristic applications. Those are the kinds of things that are going to take the most advantage of a 5G network.
Yeah, absolutely. And a question from the audience: will sub-6 gigahertz 5G frequencies pose an interference in the other bands, especially the second harmonic and the third for 3 to 3.5 gigahertz?
Obviously by design, the answer is no. If the radios are meeting the regulatory standards set on them by 3GPP and the bodies who manage these tests, then the answer should be no. But that's why it's important to test it. This is new technology. We don't know how it's going to interact, and it's very important that we don't come out with these unintended consequences. So I mentioned earlier that the importance of having frequency coverage out into that second, third, fourth, and fifth harmonic is going to be important for those sub-6 bands.
Awesome. And are TDD modulations being used for frequencies over 6 gigahertz?
Yes. From what we've seen, everything that we've measured to date in the field has been TDD signals, which for anybody not familiar with that, the difference between a TDD and FDD signal is basically rather than splitting your uplink and downlink into different frequency ranges, you're just dynamically by time changing your uplink and downlink. Or in this case, even including uplink and downlink, it's kind of an FDD TDD mix. But in this case, they are all by definition TDD. The only FDD I think that we're going to see initially is anything that's happening in the sub-3, basically either the refarming of LTE bands or some of the new sub-3 gigahertz frequency bands.
Okay, and if the UL and DL are interchangeable, and you're trying to look for interference in the uplink, how would you prevent your front end from being overloaded?
See, I got to read that one again. The uplink are interchangeable. You're trying to find interference in the uplink. Well, I will say, for one thing, we don't actually do a lot of measurements on the uplink. There's a lot of testing. That's a lot of the UE throughput testing that's done. If you're trying to find RF interference, as far as distorting the front end, I think the process all starts with looking at your frequency levels and making sure that you're looking for intermittent or in-band signals, this is another place where Rtsa comes into play, where you might have to find a signal that's within the signal you're looking for, where it might be hidden in a typical spectrum analyzer. So once you've started to identify where those signals are in, if you're trying to use a spectrum analyzer to do that, power levels can be adjusted easily. The front end of our instrument, for example, we have front end attenuation up to 65 dB. We also have a preamp built in, so you have a wide range of power levels that you can put into that front end.
Okay. And are the units upgradable with a software option if there's a lower model purchased, and would that need to be upgraded?
That depends on the option that you're trying to upgrade to. If you want to do a frequency upgrade, the frequency upgrades of our instruments are return to service center. We'll turn that around quickly for you, but we want to make sure that the instrument is calibrated and tested for the frequency ranges that you want to measure. Also, not all frequency ranges have the same front end connector. So if I bought a 9 gigahertz instrument, for example, the 9 gigahertz native connector is an N-type connector. But if I wanted to then upgrade into mmWave and purchase a 44 gigahertz instrument, now we're using a K-type connector because the N-type isn't rated to 40 gigahertz. So that's the trade-off that you get there. If you're just trying to say, let's say I bought an instrument and I want to upgrade to Rtsa, or if I want to widen the bandwidth from 20 megahertz to 100 megahertz, those things are all software updates that can be done in the field.
Cool. And are there any mapping capabilities?
Yeah, so as I mentioned, if you're familiar with our Rtsa offerings, we offer an indoor and outdoor coverage mapping through our Neon solution, which essentially is a position tracker that you use. You clip on your belt. You use it with a mobile app that then communicates with the mobile app communicates with the instrument, and then that information all goes to the cloud where you're able to get information on your coverage. So in this case, if you're doing 5G testing, you might, if you're doing a lot of in-building, you could do your in-building testing, and what you would get is a 3D map that shows you floor by floor the coverage that you have in a heat map, and then you step outside and we immediately switch in and use GPS to track your position, and you can do it that way as well.
And for 5G, why would you need 100 megahertz signal capture when as you said, the Ssb signal is less than that?
Yeah, so it's true that for certain applications you can capture just the SSB and get that sync signal block data, which is going to identify your beam. The issue where you're going to start to run into is, for one, not under the 3GPP definition, the SSB, when you start to get into the millimeter wave signals and the wider subcarrier spacing, the SSB can become wider than, let's say you have an instrument with only 10 megahertz of analysis bandwidth, which, why do you have that? You should upgrade. But you should, if you want to get wider, you can capture the SSB maybe of your sub-6, but as soon as you get into millimeter wave, you're going to start to run into problems. Also, if you want to start making measurements on your data, so you want to start getting the EVM of your data channel, you're going to need to be able to capture the wider signal.
Okay, great. So I think we have time for maybe one last question or so. So in your experience, how fast does the demodulation happen for 5G signals if we know the SSB is offset?
As long as you know the data information, obviously this is frequency and setting, instrument dependent, depends on the capabilities that you have. In our case, the capture obviously only takes milliseconds with another couple milliseconds afterwards. So, you're probably getting a fresh set of demod data every second or two, something like that.
Okay, and what does the measurement in the near field look like when the beams are not yet formed?
Well, the measurement, again, depends on what type of measurement you're trying to make. If you're trying to do a demod, you're not going to be able to get any information, because with that beam unformed, you're not going to get, without it fully formed, you're not going to get your you're not gonna get all the data you need to do that. And also the power levels that you get. I mean, if you think back to the diagram I showed where you have a radio with multiple antennas and you're beamforming, you know, if you're in the near field, there's no guarantee you're in the beam. To be honest, I'm not sure there's really a viable measurement that you should make with an instrument like ours in the near field. Now, there's some of that that's happening in chambers, in near field measurements that are actually happening in chambers. And in that case, you know, they're taking special precautions to automate test equipment so that you have an antenna that actually scans through the entire front panel of the antenna rather than trying to take any one point. You're really trying to aggregate measurements across the entire front end of the panel before you get into the far field where you have a beam.
Okay, great. Well, that's all the time we have for today, but thank you so much for everyone listening, and thank you very much for our presenter, Russell Lindsay.
And thank you.